So I'm going to talk about chips and hardware, a topic that everybody ignores. People say bare metal as though that's the bottom. That is the bottom of the OS, but it's actually the top of the chip, and there's a lot of stuff underneath there. So start with a high level, just saying there are kind of two security models. Security by obscurity, you trust the vendor, you trust certification. This is how EAL certification works. This quote here in the upper right is directly from the protection profile under which all the secure elements are certified. It says, we do not follow Kirchhoff's principle. Very clearly, it says it multiple times in the document. And then there's Kirchhoff's principle, openness, security by not being obscure. I'm not say very polar. I think both models have a legitimate place, but surely if you're trying to run something that is security by openness on the chip, it seems rather strange to have the bottom be security by obscurity. It seems to undermine the entire purpose. And I won't elaborate on that much. I would encourage you to see what Vitalik has said on this topic. He became very passionate about this last year, saying, hey, this is a blind spot. We really can't ignore this. So with that, I'll pass on to sounds good in theory. What are some of the problems, and are there solutions? I'm not going to go through the right side of this too much, but I would encourage you to think about. People would say, "Well, you publish the source materials." Okay, there's diverse source materials, and does publishing those actually enable the freedoms that you think of when you think of open source software? In many cases, it doesn't. You certainly can't build it from the source materials. You can't change it easily, and so on. So it's worth thinking about the freedoms that are supposed to be enabled by open source and considering, does open source hardware actually achieve them? There are many problems. I'm only going to delve into one. Interestingly, even legally, there's actually no explicit law or even case law that establishes that copyright is the correct type of IP for example, the initial source code. I find that very strange. Multiple people have given opinions saying, no, it really is only patent. It really is only copyright. It really is a third type of IP. I find it odd that that's not resolved. So there are many problems, and I'm only going to talk about one. The biggest problem is the verification problem. So I can publish some source, but then in the end, you get a little black rectangle in your hand, and I can say, okay, this is the source that went into that little black rectangle. Well, how do you know that that's the case? You generally don't know. So I'm going to talk about some method of verification pioneered largely by Bunny Huang. Some of these pictures are from his blog post. I put in a link to his blog post here. I don't know if the slides will be public, but you can look up Bunny Huang iris inspection and find all the materials. He's done a lot of writing on this. I can't go in depth into everything. But the idea is that there are test structures that can verify kind of the detailed, the presence of certain circuits. And then by optical inspection, you can verify the absence of other circuits. And between the two, hopefully, we can come to some better view. This is highly imperfect. This is very early days. But I always think it's better than you have a black rectangle and you have no idea what's inside it. So keep that in mind. It's just it's an improvement on the status quo. This infrared inspection is based on silicon being the appropriate level of transparency to about 1,000 nanometer. 1050 is what we're using. Chips are generally built, below this line here is the polysilicon with the doping and implants. Above this is oxides, metals. This is very reflective and kind of hard to look through. Also, it's generally facing the PCB. Normally, you would take this, flip it over, put it on the PCB. So now if you want to look from that side, you have to destroy the device. But some types of packages, and again, this is limited to these types of packages. If you have an overmold with wire bond and so on, it won't work. But some types of packages leave this exposed, and you can intentionally do this to allow this inspection. And then because it penetrates sort of moderately, you get a little bit of a deep view into the chip. And if you rotate the light source, you can begin to get sort of a view of what's inside the chip, the structure. So to talk about the rest, I unfortunately have to go do an aside on chip design. I'll try to keep this super simple. I'm just going to focus on the orange parts of these because you have to understand kind of the steps to even make sense of what is optical inspection. Chips are generally designed, the bulk of the logic is designed in what is essentially just a concurrent programming language. It looks, it's a copy on the right of some source code. It looks like software, but the only difference is it's describing concurrent operations. So that can be open source, right? It's a text file. Okay, so when you start to build the logic, you take that and try to map it into AND gates, NAND gates, NOR gates, and so on, and crucially, flip-flops, synchronizing elements that have a clock. So it's generally a cloud of combinational logic and then some synchronization, and then more combinational logic and synchronization. So it tries to map this concurrent programming language into these elements. Well, these elements are the beginnings of what you can construct on the wafer. So this has a little bit of proprietary information of the foundry. For example, just what are the cells that they support, but it doesn't have anything really physical about their factory and process. The next step, when you start to lay out, you take that, I draw in the upper right-hand corner, here's a symbol of a NAND gate. That gets converted into a drawing, and this now begins to represent the position of the dopants and the metals and so on. Now you get into things that are very revealing, very sensitive IP for the foundry because it reveals, this has electrical and design rule specs, like how close can the metals be, what is the drive strength if the channel is this high, and so on. So it begins to get into something that's very sensitive to the foundry and they don't want to disclose. I'm briefly going to say, I'm talking about just logic that can be described in this language. A chip has many, many other types of IP, and each of these is a problem. You could do a talk like this on each of these. Unfortunately, that's beyond the scope of the talk today. The one I would mention, though, that there are, I think it's actually on the next slide. After you've put this together and incorporated these other types of IP, there are test circuits also that have to be inserted. You don't want 100% of the chips to work on the wafer because that means you're not being aggressive enough in the manufacturing capability. You could shrink down and get more chips per wafer. So economically, the sweet spot is maybe 85% of the chips work because you're kind of operating at the edge of the capability of the equipment. So when the wafer comes out, you have to do what's called a circuit probe and probe all the logic and see which chips are good and which chips are bad and map them out because you don't want to put a bad chip on an expensive board and then have to throw away the board. So these test circuits absolutely are an attack surface. They can look into the memories, they can read the logic, they can manipulate. So you should be very curious about what's there, when are they disabled, how are they disabled. That's not the subject of this talk, but that's actually very relevant to security. And then I would just say, at the end, you get a series of photographic plates that represent each of the lithography steps. And making a chip is very similar to like a photography process. You would deposit something, then expose it to a light that alters, the chemicals that have been deposited, and then you would generally etch away some of what has been altered. And so deposition, etch, lithography, over and over and over, and build up these layers. So now that you are all ASIC design and manufacturing experts, let's return to verification. So in software, it's very simple. Everybody can take the source with open source IP, such as libraries, open source compilers, can essentially build the binary and look at what you're running and say, yeah, that matches, that's the source I'm running. So very simple. In chips, it doesn't work this way at all. So you start with this, this can be open source, the concurrent programming language, but then you have these inaccessible tools, always closed source IP, such as that library I was talking about that maps that into a net list. Then further inaccessible tools and closed source IP to create the GDS. That's not only the layout cells, but all the other types of IP that go into the chip, analog, IOs, memories. And then you have a very expensive process to create a wafer. You bump it and singulate it, you encapsulate it, everything's closed. There's just nothing to correspond this source to that little black rectangle. Sad state of affairs, right? So one method that has been much discussed is to open source everything up to these optical maps. If you had open source tools, open source libraries, open source IP, open source layout tools, everything up to those photographic plates, now you could, by yourself, generate something that should look like the photographic plates. Then you can, you still have to go through a closed and expensive manufacturing process and bump, singulate the chip. But as it's on the device that you get in your hand, you could inspect it and with this infrared inspection, get an optical image. Now you have something to compare. So you could say, this seems to match the kind of image of the photographic plates that I generated. So that seems like a little bit of a way forward. Unfortunately, this is a little bit more applicable to maybe low NRE prototyping flows. Foundries like Skywater, Google OpenFab, they have these processes, but it's great for open access to prototyping, but it's quite different than the process you would need to economically produce a consumer device. And I think the key thing that a lot of people not from this industry would fail to grasp is the vast difference. I use the analogy of like a 3D printer versus a Lego factory. Yeah, they can both produce an ABS plastic block, but one is viable for a business and the other is for prototyping. So some of the limitations is, this has a lot of limitation. I can't go through all of them, but it's an inexact comparison. It's just a bound on difference. Okay. And then, so we're trying to finish by 1:20? I thought it was 1:30. Okay, I'll shoot for 1:20. The problem is it has a lot of the IP of a foundry, and these are billion-dollar investments that foundries do not want to open up. So it's very difficult to approach from that. It also, if you invest in a kind of open foundry, that's only one foundry. So if we think of capture resistance, permissionless access, it's not really permissionless if it only works at one fab. Foundry portable is critical. So we're trying to work on maybe another flow where you go ahead and use this closed flow, but you redact some information from the net list, try to correspond that back to the source. One thing that is public is if a chip is made, of course anyone's free to photograph it. This is an object in the world. You could photograph each standard cell and make a library of photographic images that you took publicly. Now this is public information. So with this kind of redacted net list, you could patch together what I call a quilt or a pseudo GDS, which has, now it has a documented correspondence back to the source, and you can compare that to the, to what you see in your hand, and you actually have a tie all the way back to the source. This is probably plausible even with, TSMC and so on. Yeah, I'll skip over this one. I would say these are very early days. This is really inexact and has a lot of problems. We don't even know that we can necessarily get there. But anything at all is better than a black rectangle. And I think this problem doesn't go away by just ignoring it. I feel like in software or maybe an event like this, there's a little bit of what I call the lost key syndrome. It's like, this is too hard. We'll just look at the software because that's easier, whether or not that's really where the problem is. So a couple subtle points. You think about the trade-off between open source and available component. At some point, rather than relying on open source, you rely on you're able to procure something that's very generic from any source. And at some point, you're down into that world, no matter how much you open source. There's, even in that top flow I described as maximally open, well, then you go to machines, and they have process recipes, and then they buy chemicals. These absolutely affect the behavior of analog cells. So at some point, do you have open source aluminum? I mean, at some point, you have to stop and say, no, this is a generic thing that I can procure anywhere. You have to be thoughtful about that boundary. And then there's a trade-off between open source and decentralization. On the network side, you say we try to abstract away the hardware by being decentralized. If you try to be private and do compute in your hand, you inherently are more dependent on chips. Okay, so to finish in 2 minutes, what Crossbar makes is a chip that is kind of like an MCU and secure element in one chip that is, let's say, very open source, more open source than any other chip. Here are the links to the repositories for the hardware, the chip RTL itself, that concurrent programming language I described, and also the SDK. We encourage you to look at it, develop on it. We thought this is an example of how client-side can empower you to do private compute. For example, you could do an MPC calculation between your phone and our wallet. It's all happening. You could hold a threshold of shares in your hand and do kind of a private computation that way. So we think it's privacy enhancing, security enhancing. Generally, we call it security processing unit because it's meant to be a platform for innovation, high power compute and a cryptography engine under an umbrella of physical countermeasures and in open source. So I'll stop there and say if there's any question. Thank you.
Thanks, very interesting topic. Maybe for a person who doesn't know much about verifiable hardware, is it possible to, let's say, come up with some software solution where you have a program that is supposed to be running on chip and you benchmark different things like the speed of execution of different operations and maybe something else, and then you maybe don't get a full confirmation that this is the chip that you thought it is, but maybe at least it's some, if there is some obvious problem with it, you identify that it's not this chip?
Yeah, you could benchmark that you have an authentic copy of a certain chip and that it's like other chips that have that same top marking, but you can't correspond, you still have no idea what any of them are. So somewhat, yeah, you can maybe verify uniformity, but not tie it to the source. Yeah.
What about formal verification?
Yeah, so I think the place for some formal verification methods in formally corresponding that source to the redacted net list, but it's limited because it doesn't have all the IP in there that goes into the chip. Yeah, I think that's the nut of the problem is how do you formally tie it to the inputs? Yeah, it can be done inexactly.
I'm curious how difficult or what is the information you're glossing over when you say take a picture of the chip at the end and do a compare to a previous intention? Because you would need equipment that has adequate resolution, and then you would need some process to be able to do a compare over the vast at that resolution pictures.
Yeah. So again, if you think about, I didn't, maybe if you did the math in your head, 1050 nanometer, okay, that's not 1050 nanometer infrared, and we're at a 22 nanometer gate length. So even as you move this across and try to get kind of like a deeper view, it's very inexact. The point of focusing on that was that you could do it, we're building a setup in our lab, for example, you can do it for under $100 or something. Now, if you want to go fancier than that, yeah, there are, you can use X-rays or something like that, but then it becomes not accessible, and there's a big trade-off there. Also, Glossaur doesn't, the analog cells, the memories, the insertion of the test logic, which is sitting there and wasn't in the source, it's a big mess. I would say, again, think it's better than just a black rectangle, but these are early days. I like what Vitalik said. He says, it's difficult, but we have to go there. It is difficult, I can't say.
Okay, well, we're going to leave it at that. And so thank you very much.
Okay, thank you.